Okay.
Okay, so hello, good day, good evening to everyone. Welcome to another episode of Stark at Home. This is a project that we started when we all had to start staying at home with the COVID situation. And for better or worse, it's been going on for quite some time. And this is a very special episode, not just because it's the opening of 2021, but we have a very special and esteemed guest that I'll present in a minute. For those who don't know me, I'm Eli Ben Sasson. I was Avi's PhD student, among many others. I'm also a co-founder and president at Starkware. We're doing a lot of stuff around zero-knowledge proofs and making them available to the public. I'm going to share some links if you want to do more stuff like program code that can be automatically generated into Stark proofs and put on a blockchain. It's something that we just opened last week, so you can later on, not during this, go to this playground that I just shared. And if you want to hear more about this system called Cairo and how it's going to revolutionize blockchains and make them more scalable, you're welcome to hear me talking about it next week at the Real World Crypto Conference. And now let's go to the matter, the topic of this week. So many of you attending probably know of Avi Vigdersson, one of the most amazing theoretical computer science researchers of the past, I guess, 40 or 50 years since he's been active in that area. As I said already, he was my PhD advisor. Wait a second, I just have to ask, can you hear me? I haven't checked this. So can someone just type, can you hear what I'm saying? Hello, can you type in the chat if you hear? Okay, good. Thanks, Adia, Leo, and Edna. Okay, so as I said, Avi is one of the most amazing researchers in theoretical computer science and has contributed to almost all of the important advancements in that field, be it de-randomization, proof systems, and many other areas. He's also contributed significantly to 35 years of proof systems, and he's going to share with us his reflections on this. The one thing I'll say about him, he has a long list of prizes and so on, and Evalina, Gödel, other stuff, you can find it on Wikipedia. The one thing that I think, the first word that jumps to my mind with respect to Avi is his optimism, and the second is his enthusiasm about research and life in general. That's what drew me back in the day to theoretical computer science and to working under his advisorship, and you'll see all of that today. One minor thing is there's this, if you want to ask questions, so I'm now going to hand it over to Avi. If you want to ask questions, please use the Ask a Question button, and once in a while, Avi's going to pause and answer some questions that I'm going to read to him. And without further ado, Avi, please take it.
Okay, so let me try to share the talk to make sure this works. All right, everybody can see this. I cannot see you. Yes. I cannot see the chat, so Eli will...
Yes, I think this is all fine. We can all see it, but if someone can please, can you see this split screen with Avi and his talk? Yes, okay, so please go ahead.
All right, good. So I want to talk about this value of errors in proofs. I'm really happy to be here. It's a very different form than most lectures I give, so I hope it works well, especially as I don't see anything. So the plan, Eli gave me an hour, and the plan was to tell you about the title and the amazing things we get out of allowing errors in proofs. The scientific impact it has on lots of scientific areas, the practical impact it has on lots of systems, and the conceptual impact, which is maybe the most interesting, the kind of paradoxical properties of proofs we find if we allow errors. And then I realized that I have to explain errors, and then we have to talk about the value of errors in computations. And to do this, we have to actually talk about proofs and about computations and their relationship, which play an essential role. And I'm going to do all that. And I also want, this really important part of the plan to do it in a way that highlights the value of the complexity theory methodology of classification and completeness and modeling and impracticality, ignoring practical issues in the development of this understanding that many of you know and use. Okay, so let me start. If anybody wants to read, that's a book that talks about this methodology and in high-level form, that accessible, I think, to many. If you like the cool cover design, you can buy it, but anyway, it's free online on my website. Okay, proofs and computations. This is a long story. I'm going to give you just 2 points in this long collaborative history. One is Euclid, 300 BC. He wrote the Elements, which is an amazingly influential book, in which he has many theorems in plane geometry, which are proved by deduction from 5 simple axioms. So that's the proof part. And these are basically the same, or the way the proofs work is by computation. They are constructions of point sets in the plane using very simple gates, or just using ruler and compass. So they are already tied together from the beginning of time. And jump to the turn of the 20th century, Hilbert, maybe the most influential mathematician ever, had a dream that he pursued for several decades, that truth in mathematics is the same as provability in mathematics, and it's the same as computability of proofs. And his dream was shattered, badly. Nevertheless, influencing us. First, Gödel came and with his incompleteness theorem showed that there are truth facts, let's say, about integers that can not be proven in any system. And then Turing came and with undecidability theorem showed that proofs and computations are different. And I want to talk a bit about this. Of course, Turing's paper, you have to appreciate it. He was a PhD student. He defined algorithms using his famous Turing machines. Side corollary of this is the computer revolution we all experienced since. But I want to talk about the theory. And I know that the audience has many people who know how to prove everything I say, but there are also many people who are developing systems and do other things for fun. And I want to nevertheless develop some terminology and talk about this theory in a way that will be useful for me later. In particular, talking to Eli beforehand, the level of formality of the talk. I'm trying to talk to all of you, which is sometimes means that I talk to none of you. I want to talk about complexity classes. So there will be this, we love acronyms for classes of problems. But I want you to see the value in this. So you don't have to like it, or you don't even have to understand it. I'll talk in high level language enough, but I nevertheless want to use it. So first of all, what kind of problems are algorithms supposed to solve, or what kind of theorems proofs are supposed to prove? Well, they each correspond to some set, and the kind of what we call decision problem is is an object in this set. These are the kind of questions we ask to solve by programs, and this is the type of claims, X is in S, we ask to prove or to be convinced of. And Turing defined two important sets. The recursive sets, those sets that are computable by finite algorithms, and the recursively enumerable sets, which are the sets provable to finite algorithms. So both are defined in terms of algorithms, so we see the connection again. And it's clear that everything you can compute, if you can compute something, you don't need anybody to prove this to you. So the second contains the first. And his main theorem was that these two sets are different. That's how he shattered this second part of Hilbert's ring. And the way he did it, he just found one set, that is recursively enumerable, but not recursive. And this is the famous halting set of Turing machines which halt on empty input. And I have at least three reasons to have this notation. One is that it will appear in the last slide magically, and unexpectedly, and with amazing influence. The second is that it sets up complexity theory very easily. If you just replace finite by efficient, you get the sets P and NP. P is a set of It's a collection of sets that are computable by efficient algorithms. NP is a set computable by provable to finite. Oops, what did I do? I managed to. Okay. Provable to efficient algorithms, and it sets up the very basic question that we still seek, understanding whether P equals NP or not. So the same question of probability versus computability in the efficient regime. In this definition, efficient means polynomial time, but it's clear, and in fact, everybody uses all the variations possible that are relevant to any applications or theory. You can define any resource bounds on your algorithms, and that's what we would call efficient, and still you get things that make sense and very great questions. I just want to say about the P versus NP question, you can care or not care about it, but you sort of believe it, because without it, there is no cryptography. So it's something to remember. Okay, so now I want to just walk you through, just to understand what, claims, arguments, proofs, proof systems, provers, verifiers, through examples of these, so that we get, familiar with the diversity of this. And they are supposed to capture, the questions we are interested in. Of course, this sort of questions pervade since antiquity. What is true in real life, what is true in mathematics, when is an argument convincing? And in all this setting, the type of claims will be what I said, some object is in some set. And, you want to be convinced of that. And the objects can come from arbitrary universes, and, the sets just say, an object has a particular property. Okay, so let's see some examples, and actually I have three examples, and I'll run through them twice. So here's one type of claims, the volume in the left glass is bigger than the volume in the right glass. So the input, the object is a pair of glasses here. And, there's a way to check it that you probably know. Of course, you can measure them and compute volumes and so on, but what most people would do is this: they'll fill the left cup with water to the rim, pour it to the right cup, and see whether it spills or not, say yes or no. Very simple. Here's a very different type of claims. This Sudoku puzzle is solvable. You can try it, but maybe it's hard, but anyway, if you just want to be convinced of it, here's a very simple argument. Just filling the rest of the squares. Of course, you don't have to believe it, and you shouldn't believe it. That's the whole point. You should verify such an argument, but it's easy. You check, the Sudoku rules, row, column, squares, and you also have to check that it's consistent with the input given to you, and decide. Another example is that claims of the form, this number is composite. It's a very big number. What would be an argument? A pair of numbers, and bigger than one, of course. And verifying such an argument, again, is simple. You just multiply the two numbers. So that's familiar example. So let me run through these arguments again and make some observations about it. In the first, the verification that we went through with the water is actually a description, a very good, almost formal description of procedure you should go to. And this procedure is a general procedure. I mean, it doesn't work just for these two glasses, right? It works for, lots of pairs of glasses. Of course, you have to be careful. Everybody who's programming remembers that you have to have the input satisfy some properties, or maybe the rims have to be flat. But anyway, there is a general procedure. There is a proof system for proving such claims. In Sudoku, it's the same. I mean, there is a simple, efficient algorithm, simple pattern matching that would check any argument, so it's general. And also, in general, in the sense that you don't have to just think of a 3x3 example. There are 4x4. I mean, inputs to this proof system can be of arbitrary size with the same meaning. And the third is in the case of composite numbers, again, verification is a simple algorithm. It's general. And we didn't talk about where the argument comes from. Of course, we see it's short, and but maybe it's hard to come by, and we don't care in proof systems where arguments come by. They may be hard to come by. In fact, in this particular case, cryptography relies for many years on the difficulty of finding such arguments for this proof system. And another thing is that you should start, if you think about these as proof systems, you should start getting used to calling claims that were proved this way theorems. So, this number upstairs, it's a theorem that it's composite. If you want food for thought, you can think about developing a proof system of the same nature with short arguments that are easy to verify to the complementary claims. Let's say that a number is prime. But I don't want to talk about that. These are a bunch of examples, very different examples of what I want to call proof systems. And people try to formalize them, and especially logicians. So deductive proof systems, in fact, we've seen one, or I talked about one example. This is Euclid's system of proving facts about plane geometry. The objects are more or less shapes and lines and points. If you want to talk about integers, and a famous important example is piano arithmetic, and that's in general how deductive proof systems look like. There's a set of objects, here's formulas or expressions over integers. There's a set of axioms. There are things that you should accept because they are obvious, like addition commutes or x plus 1 given than x, and so on. And there are deduction rules. If you know already, if I prove to you A and I prove to you already that A implies B, then I really prove to you B. These are things you have to accept in any situation. In some sense, in any proof system, you have to believe or trust something. I mean, even in the case of compositeness, you have to believe that your multiplication algorithm works. Or in the case of the glasses in water, I mean, you have to believe that the volume of water doesn't change over time or when you pour it. So there have to be things that you believe in, and then proofs are basically reducing complex statements to these simple truths via these simple sound steps, the deduction rules. And then an argument in these systems look like just a sequence of formulas. And the verification procedure is, you go through each one and check either it's an axiom or it follows from previous things proven by one of the deduction rules. So that's how verification looks. And amazingly, I mean, with such a simple beliefs and simple deductions, you prove amazing theorems, like that there are infinitely many prime numbers, or that, while Fermat's last theorem, and so on. Now, this is a particular proof system, and logic is full of proof systems. There are books and books with many systems, with many sets of axioms and different deduction rules, and all have this, this structure, but they are different. And the question is, and they are also different from the examples I've shown you before, with Sudoku, for example. And the question is, how do you capture all of them? So the main, one main point I want to stress is this complexity theoretic view. And first, let's summarize the essence of what all of them have in common. So what are the essentials of all these proof systems? One is what is called completeness. It's just true claims should have proofs. Second is soundness. False claims should not have proofs. And the third is distinguishing the two, right? I mean, you should be able to distinguish arguments, whether they are convincing or whether they are faulty. And this verification should be done efficiently. This is a property of all the examples of all the logical proof systems that we've seen. And this has a very simple and natural, but very powerful view in complexity theory that was given by Cook and Recha. This is the same Cook that you know and love from NP completeness. In fact, you may remember even that the name of his paper on NP completeness is called The Complexity of Theorem Proving Procedures. So he was interested in that. So in his paper with this student Recha, he defined what all these proof systems are. And the key thing is that an algorithm defines a proof system. This is this verifier. It's just an algorithm. It's an efficient procedure. It has takes two inputs. One is a claim, and one is this argument for the claim. And it should satisfy the two properties we talked about. One is completeness. If the claim is true, some argument makes this machine accept. This is a happy case, right, in which a claim is a theorem and the argument is a proof. And soundness, which the case of the claim is false, and then no argument can convince the verifier. Every argument causes rejection. This is a basic two properties of any proof system. Once we have this, I said should get used to calling claims provable in any such system theorem. So let's call it so that this T sub V is just the set of theorems that are provable in this particular system defined by V. And what they observed really, because it follows the basic methodology, is that NP, the same famous class NP, is simply the collection of sets of theorems provable for any deterministic polynomial time algorithm. Okay, so it's a different characterization of NP in terms of proof systems, which capture all the properties we talked about. So all the proof systems we talked about are examples of members in member sets in NP. Okay, I think I promised Ellie to try to every 15, 20 minutes let people ask questions or pause or let you reflect, and Ellie will tell me if anybody wants to ask anything.
So I added just one question, but I want to have others ask. So in your slide there's claims and theorems. So can you clarify if they are the same? And
no. So I want to stress. A claim is anything. You can claim that it is nighttime now. Maybe in some of for some of the listeners it is. So anybody can claim anything. A theorem is something which has a proof. So an argument which convinces the verifier in this proof system. So a proof system is defined by an algorithm, verifier, and the verifier, the behavior of the verifier determines what are the theorems and which of the claims are theorems and which are not. The claims which are theorems are exactly the ones for which there is an argument convincing the verifier, and the others are the ones that he's never convinced by any argument. That's what separates theorems from non-theorems in this particular proof system, and that's true for any proof system.
Okay. If there are any other questions, I suggest we continue, but please use the Ask a Question button, and we'll take them in the next question session. Okay.
Okay, great. So we are at the point where we are going to get to introducing errors into proof systems. And that's where we start the real talk. But as I said, before we introduce errors into proofs, I want to tell you what you basically know about is introducing errors into algorithms. But this is very fitting because proof systems are defined by algorithms. So it will be very easy and very natural once we have this view of proof systems. So let me talk about this. Probabilistic computation, errors in algorithms. It all starts, I guess, in ancient times, right? I mean, the observation that nature seems to provide us with free access to randomness. It's something that everybody always knew. It existed long before complexity. Statisticians used it, and for sampling, for lots of purposes. I'd say since antiquity. I mean, it's well known that shepherds knew how to estimate the number of sheep in their herd. They didn't have to count the number of heads. They could count the number of legs and divide by 4. Well, maybe that's not the best example. Anyway, there is this resource that benevolent nature seems to give us. So let's use it in algorithms. So let algorithms make random choices. These are probabilistic algorithms. And what I want to stress is that given that you decide to do that, the output of your algorithm becomes a random variable. So I want to contrast deterministic and probabilistic algorithms and nevertheless show their difference and their similarity. So say you want to compute a function, in a deterministic algorithm, we say that the algorithm computes it if for every input, the algorithm on that input equals the function value of this input. A of x equals a of f of x always. In a probabilistic algorithm, B, the output is a random variable. but you insist that b of x equals f of x with high probability, you'll see this WHP a lot with high probability. I write here high probability as 2/3. 2/3 has, an important meaning. The meaning is that 2/3 is bigger than a half. Whenever it's bigger than a half, at least you know what B thinks. It's unique what value it thinks. Maybe you will not get it in some random run of the algorithm, but it's defined. And the other, you don't like 2/3, and this is a key thing. This is property that this holds for every input, means you can amplify, you can reduce the error arbitrarily, and this is key. This is key both for algorithms and for proofs. Errors can be efficiently reduced as much as you want. You want 1 in a million, you want 1 in 2 to the n, no problem. Just take your algorithm, run it a few times, and take the majority vote. And then the new algorithm will be also efficient and will have tiny error. So it doesn't matter. When I write with high probability, you can put there whatever you like because it's equivalent. Now, you can ask why even consider introducing errors in algorithms. It's a good question. First of all, the rationale for using probabilistic algorithms is the axiom seems reasonable. Debating it is a great hobby of mine, and I give lectures on it, but not now. And the second is that, we tolerate uncertainty in life everywhere, why not in algorithms? So, in fact, people use, and most of you use probabilistic algorithms without even thinking about it. And why do we do it? Because it seems the value here is clear. We seem to be able to solve many more problems using probabilistic algorithms than we do using deterministic ones, and in simpler ways, etc., etc. So that's the value. And there's more value, but again, it's not the topic of today's lecture. So now let's see about introducing error into proofs. But it's the same way, and I'll do it in 2 steps. I want to stress this is I'll do it in 2 slides. These are, earth-shattering, papers of simultaneous from different motivations, one of Babai and one of Goldwasser, Mikali, and Rakov, that take the Cook-Ratcher framework and say, let's throw in randomness. So let's make our verifier probabilistic algorithm, just like before. And, demand that, in the case that the claim is true, some argument that convinces the verifier. Always, you can put with high probability there also, it doesn't matter. But the important thing is, in the case that the claim is false, you allow an error. You allow an error in the rejection case. Now, I want to say that this is somehow, even though the modification is obvious, there's something that is certainly to mathematicians or to people who think that proofs are, these wholesome beings. These are things that are always true. This is mathematics. Theorems are, convey truth. How can you allow error? This is not about running an algorithm. So this is a major, conceptual break, allowing errors. But nevertheless, you can do this, and you can define the same way. There is a set of claims that are provable in the system in the same way, and we can call them that. And IP, like NP, is the definition, just as a collection of these sets for every possible probabilistic verifier. And the next slide is going to say that we allow V to be probabilistic, but in these papers, they also added interaction. The way the access of the verifier to the argument is different than before. It's not just reading the argument. And this is the second important ingredient that I'll put in a picture next. Here's how they view it. We call it IP because it's interactive proofs. Probabilistic was taken for granted because randomized algorithms were, no. So here's how it looks, and I want to contrast it in the same way I did with the deterministic ones before, in the case of algorithms. I want to first think of how NP looks like, the proof systems for deterministic verifiers. Here, by the way, is a suggestion of Babai to think of the verifier as King Arthur, with those who like the search for the Holy Grail is sort of, looks baffled or stupid or anyway limited. And the prover who supplies the proof, the argument, is an all-powerful magician. We said we don't care where the argument comes from. It can come from any being who has arbitrary powers. But the verifier never trusts the prover, so needs to verify. So NP is a class of proof systems where claims can be verified by a deterministic algorithm. And I want to stress that in these deterministic cases, the interaction is very simple. There's just one message. They both see the claim, there's just one message, the argument for the claim. In interactive proofs, we allow the verifier to, challenge the prover, to ask questions. And there may be random questions. It's probabilistic, it can ask random questions. But still, at the end, it has to decide whether it accepts or rejects, and it will do it correctly with high probability, any probability you like. So I want to say that, on the face of it, this is a, reasonable definition for proof systems. I mean, if we accept this tiny probability of error, what else can we accept probabilistic algorithms? The only other thing we have to accept is the possibility of interaction, which is very natural. In fact, as I mentioned in the paper, interaction between, just in the classroom where, some professor is proving to the teacher, proving to the students something. They may ask questions, they may challenge, they may, basically interact. So this is entirely reasonable. The only thing is that the verifier is still an efficient procedure and can never be fooled into believing a false claim, except with a tiny probability that this is what we accept. Okay, so these are interactive proofs.
Avi?
Yes.
There's one question on the previous slide that I'd like to read to you. In the probabilistic proof system definition, can you flip and have accept with high probability but reject always?
No. No, it's it's a key thing. You have to allow a tiny probability of error. Allowing error in the completeness case doesn't really matter, but let me not go into it. But yes, it's absolutely essential that we allow sometimes to be fooled by false arguments, but we control the probability at which this happens. We can reduce it arbitrarily to 1 in a billion, to exponentially small, but it will always exist. Mm-hmm. And this is what we allow, and the question is, what's the value of this? This is what we are going to explore now.
Mm-hmm. There's another question.
Yes.
By Abida. So far, we haven't said anything about the size or running time of V, right? V could take really time.
I said that for this talk. For this talk, I said that when I say efficient, I mean polynomial time. So, but I also said, and it's important and was used, that you can take all these definitions and impose different resource limitations on your algorithm. You can say it's space bounded, you can say it's energy bounded, you can say it's communication bounded. Many of these changes are important and were done and were studied, and some are understood and some are not. I'm just keeping for me, efficient here is polynomial time.
Okay, one more question. Can you please say what is the probability space?
Yes, the random choices of the algorithm. The algorithm, as we hypothesize, have access to, randomness in nature, which, in fact, like probabilistic algorithms, it's the same thing. You assume you have some access. It's an assumption. I stress it's an assumption that anybody using probabilistic algorithms is using, that there's some source of random bits that, are probably hypothesized to be independent and unbiased that they are using. Every statement, every theorem about probabilistic algorithms, probabilistic proofs, assumes this probability space. So you can assume the probability space is just access to an arbitrarily long string of independent, unbiased coin tosses.
Mm-hmm. Thank you.
Sure. Okay. So they made this suggestion, and they came from different motivations. Babai from group theory and Grobler, Mikhail, Rakov from cryptography. And they both wanted, they already expressed the value of this more general proof systems. And so I said, and I mean, as you see it unfolds, it's an absolutely revolutionary scientific notion. So that's what I want to talk about now. So the value, you'll see it, I elaborate much less than I can about all these conceptual, scientific, mathematical, and technological impacts. I'll mention some. And more I want to talk about the proofs that can have, because of the error, paradoxical properties, zero-knowledge proofs, which say that convincing proofs need not convey information, and PCPs, which say the proofs can, don't really need to be read to be verified, just glance at them, and that's it. But even more, I want to say that despite the fact that these two notions are very, very different in many ways, and I'll explain, there was a journey that took us from the first to the second, and I want to talk about this again through the complexity theoretic methodology. So let's start with zero knowledge. In the same paper, Goldwasser, Mikhail, Rakov suggested the following. We look at interactive proofs, and we want to impose another property. It's a zero knowledge property. This is, it's just interactive proofs plus the demand that if the verifier accepts a claim, then it learns nothing else. So it learns that it accepted it, so it believes it to be true, but it learns absolutely nothing else. And then you have to stop. I mean, Eli told me that today there are packages with zero knowledge that people use like they use hash functions. I mean, you have to think about the meaning of this. I just want to, first of all, say that formally defining this notion, what does it mean that the verifier learns nothing else, is a highly non-trivial issue, which they do. But I'm not going to go there. The intuition that you have is the right one. You just have to define it. You just stare at this and you wonder, how can this ever be possible? I mean, how can a convincing proof be uninformative? When was the last time you convinced anybody of anything without giving them any new information they didn't have before? So the motivation, as I said, was cryptography, and they hope that this can be done maybe for some special types of claims. Maybe if you want to prove that your RSA key is composite, which is essential to security, say, maybe this you can do in zero knowledge. This was a kind of motivation. But if you think mathematically, if you talk to any mathematician, say, how can Wiles convince the mathematics community that he proves the Fermat's last theorem without giving them anything, any information they didn't have anything about the proof. So what types of claims, what type of theorems can be proved in zero knowledge? Turns out every kind of claim, anything provable at all, anything in NP, which we said was, the collection of things that are efficiently verifiable, anything like that can be proved in zero knowledge if you have one-way functions. The most basic assumption of cryptography allows for that. So in other words, if you have a proof, it can be turned into a zero knowledge proof, any proof. So there are several things to say. There's so much to talk about if we just talk about zero knowledge, but since I have a few more things to describe, I want to stress one thing. This theorem assumes crypto. And it is a question of whether cryptography is necessary that leads to the next step. We know, Ostrowski and I have proved that in this context, in the interactive proof setting here, it is essential. Non-trivial zero knowledge implies one-way functions. But maybe you can, we changed the model once, let's do it again. So this is exactly what happened next. I promised to, let me go to this in a second. I do have a slide on some impact. So in a subsequent paper, we showed that having zero knowledge proofs is very powerful to cryptographic protocol design. You can imagine this easily, right? Because not just proving your RSA keys composite without revealing the factors. In general, you don't have to worry about, when you design a protocol, about parties that deviate from the protocol, because you can ask them at every step to prove to you that they acted correctly. Of course, it entails their private inputs, but they can do it in zero knowledge, so that's no problem. So it's a very powerful mechanism design. But at the same, paper and every lecture I gave on this, I stress, it's all, theoretical. Nobody is going to implement the zero knowledge protocol. I didn't say anything about the proof of the zero knowledge theorem, and I can say at the end, if you ask me, some words. But, I stress this is impractical, and then, years passed, and lots of my friends, in fact, Shafi and Silvio and Eli and and many others, probably many among you, put me wrong. There are zero knowledge, as I'm told, is a word that venture capitalists understand and love, and things like this are being implemented in systems. So it is practical. People took it in different directions. You don't have to think about algorithms and systems. They are physical. The notion, you can take it to physical zero knowledge proofs. There's an amazing paper on using it for nuclear disarmament verification of between US and Russia. There are physical systems for testing in zero knowledge DNA, comparing DNAs for forensics, for example, and more. And what I do want to continue with is how it, generated new proof systems and the power of these. So let me go back to this and talk about that paper.
Can we ask, there are two questions about zero knowledge.
Yes.
Okay.
Good.
So the first is, you left us with a mystery. How can a proof be non-informative? Can you give a hint as to how that can be possible?
Okay.
Oh, wait, and I'll already read the second because maybe they'll be together. The second question is, could you please give an example of a zero knowledge proof?
Yes. Okay. So.
Wait, and well, the third is also related. Can you define non-informative, or do you mean an incomplete proof? So, like, what?
No, it's complete proofs, and yeah. So I'll answer them all together. I'll answer it briefly, and then at the end we can elaborate. The example of a proof a zero-knowledge proof I gave. I can take Wild's proof of Fermat's last theorem, and I can convince any mathematician of this without letting him see anything from the proof. I can take a complex, I can take a large number and convince you it's composite without showing you, or giving you any knowledge about its prime factors. So I gave these two examples. I can take any NP-complete problem, formula, and convince you, assuming it's true, assuming I have a satisfying assignment, I can convince you that it's satisfiable without telling you anything, without you learning anything about the assignment or anything else you didn't know, and still you'll be convinced, even though it's an NP-complete problem, that it's satisfiable. How it is done? It is all about the locality of computation. It is all about the fact that verification is local. There are two essential ingredients. First is the use of cryptography. You can just encrypt each part of your proof, like each part of your statement in your logical proof system, when the verifier wants to check it. Encryption, we know, it's like random junk. So how do you test it? Well, you can check one of the deductions. You can just want to check that, some statement is an axiom or follows from two previous ones. And you randomly pick one. Clearly, if my proof is wrong, one of them will be wrong. So you'll catch me with some non-trivial probability. And so that already talks about catching false proofs. It's not satisfying in terms of the chances, but you can repeat it many times, and then you can amplify it as much as you want. The problem is, why doesn't it reveal anything? And that's the non-trivial part here, is that if you have a proof of any statement, if I really had a proof, I can generate it, at least in some proof systems, I can generate from it a distribution of proofs. So if I have one proof, I have many, and this distribution has the following amazing property, that any local view, anything that you check locally, like you check a particular deduction, what you find there is exactly what you expected, that the deduction is legal, but it's a random deduction of meaningless things, something you could have generated yourself. So it's hard to expect that you'll understand what I said without more visual aids or more time. So let me stop at that. I'll be happy to give a talk with the proof of the zero-knowledge theorem in another forum, or talk about it more at the end of the lecture. Okay, Eli?
Yes, of course, sounds good.
Okay.
Yes.
Yeah. So, it's always sort of said to, like in magic tricks, when you reveal the way the magic is done. But anyway, that's the key. Cryptography is the key. Locality of computation is the key, and the ability to make from one proof a distribution of proofs so that every local thing you look at looks random. Okay, good. So let me move to proof systems with many provers. This is something that we proposed a few years later. What is the setup? Well, it's another extension of the previous proof systems, but now instead of one prover, you allow two provers. So the verifier interacts with both of them about the claim and eventually decides to accept or reject. And, there's a set of things that are provable with these systems, one for every verifier, like before. This is what we call the class 2 IP. And you can have 3 provers and 4 and, MIP for any number. So why, let me stress, these provers, can talk as much as they want before the interaction, but after that, they are physically separated. And that's a key, like in the prisoner's dilemma, when you interrogate 2 prisoners in different rooms. That was the logic. And the motivation for this was exactly the question of whether there is a setting in which you can have zero-knowledge proofs that do not use cryptography. And that's exactly what we did. We proved that all of MP has zero-knowledge proofs in this, more general proof system, in which physical separation replaces the computational assumption. And this was our motivation, and we were satisfied. I mean, this is, what we set out to do. But the way complexity theory works, and that's what I want to stress again, is that it never stops there. Here is what, just the methodology tells us to think about. These are classes, the things provable by deterministic algorithms, by probabilistic systems with one prover, with 2 provers. They're just sets of problems. There are computational problems, and we can ask, where do they live? How hard does it to compute whether X is in S for one of these things? And people, of course, began studying it. There were trivial things to notice that, there's some complexity upper bound on how powerful the statements they could prove are. I mean, like, how much do you buy? What's the value of adding this interaction or interaction with many provers? And we had a few hints that, it looks like these inclusions were an overkill. It looks like these new proof systems could do just a little bit more. We had very few examples where it seems that they can do something beyond NP. And then there were a few years of stalemate. And then, what happened because of work in other areas of complexity and cryptography and so on, suddenly this community that for so many years and decades worked with discrete structures and combinatorial arguments, discovered polynomials. Now, it's not, I'm exaggerating, we were working with polynomials all the time, and what was really discovered is how much more you could do this with polynomials than you thought. This was extremely highly non-trivial technical things. Once this happened, there was an avalanche, a real avalanche of characterizations of these proof systems. And in fact, they turned out to be as strong as they could possibly can. IP, much above p-space, much above MP, it's p-space. 2-prover IP is non-deterministic exponential time. And I'll get to the third, but I want to say that, if you don't like these acronyms, they all have conceptual meaning. What the first one says is that things like winning strategies are efficiently verifiable. Somebody can come here from Mars and tell us that they have playing white in chess, they have a winning strategy. This is something we have no idea how to have a short proof for. But IP equals p-space says that there's, we can check that. Not that they win against us every time. I'm not talking about this. We can verify that they have a winning strategy. This is amazing. Even more amazing is the second, another reasonable proof system in which, non-deterministic exponential time is already way above p-space. It contains intractable problems that require exponential time, Even these are efficiently verifiable. And this sends a very powerful message that was taken next, that, if, they take exponential time, proofs have to be exponentially long. It means somehow the prover, which is efficient, polynomial time, is not looking at the whole proof. And that led to the definition of PCPs that I'll do next, but I'll just summarize. This result, PCP equals NP. One way to understand it is that written proofs, like mathematical proofs, are verifiable without reading them. You just need to glance at a constant size snapshot. And for those developers who are, don't care about mathematical proofs, but certainly care about verification of transcripts of program execution, it's the same. You don't have, starts, for example. You don't have to look at the program execution, at the transcript. You can verify it just by glancing at a little bit. Another thing to stress is that there is no crypto in these results. Definitely not at the last one. Okay, so it's very different nature than the zero-knowledge theory. So what are they, these PCPs? Well, I mean, we are back to this story. Now we are talking about no interaction. The prover just sends an argument. It's just a written proof. But the verifier is probabilistic. It tosses coins. And the strange and sort of, again, unbelievable demand is that we allow it to look, let's say if we want probability 2/3, we allow it to look just at 20 bits of the argument, even if it's 100 pages long, or if the transcript of the computation is, trillions of bits. So again, like with zero knowledge, how is it possible? I mean, how can you find a bug in a proof or an error in a computation that's very long by looking at a tiny part of it? I expect somebody will ask me. So you can wonder whether it's useful for anything, but I already told you the theorem. The theorem is that everything provable is provable in this fashion. It's verifiable by such a verifier. So every proof can be turned into a PCP. Anticipating the question, let me say just a few words about how this is proved. And again, it is about locality of computation, and it is about error correcting codes. At least the intuition for it can come from error correcting codes. So if there's a bug in a very long proof, you can think of it as a sequence of zeros that should be all zeros, zero, let's say, being this step is correct, and this step is correct, and this step is correct. There is only one bug that's, a single bug that you want to catch. But if you error correct transcript, or you error correct a proof, then, every single bug or every error, that's the whole purpose of error correcting proofs, will be smeared all over, and then you can catch it with a random spot check. But that's, it may be a beginning of an idea, but it's, it sort of stops there. I mean, why should the verifier believe, or how can you check that this is what you got, what this long sequence is a word is a legal word in a code? That's where all the problem is. Anyway, so let me again say this. Maybe I'll pause for a question.
Yes, there are a few questions, but yeah, you wanted to say something, so say it, and then we'll.
No, I'm open for questions.
Okay. So there are 3 questions. One is, here's a question: why is it that moving from 1 to 2 provers has this jump in complexity classes? And does it continue when you go to 3 provers or more?
That's a great question, and
thank you. I asked it.
Yes, just take the intuition of the prisoner's dilemma. Compare yourself with a police officer, which in one case has, one criminal which is trying to get either a confession form or what happened at the scene of the crime, or where you have two people you suspect have committed something and you are trying to get from them, but they cannot talk to each other, and you can tell each one a story about the other. I mean, the whole point about two provers is that they need to be consistent. Consistency is the name of the game. When you have one prover, there's no way to check consistency against anybody else, and that's the relative weakness of one prover from two provers. If you continue to three and more, it depends on the setting. In this setting I'm describing, it doesn't matter, but for many purposes, it does matter, and some I'll talk about in the last two slides.
So I guess maybe as in marriage, being consistent with respect to your kids when you're alone is much harder than is much easier than trying to be consistent with your spouse as well.
In any aspects of life, I think consistency is, well, it's a great asset if you have it, and you can check for it. Yes, this is the key to the power of two provers over one prover.
Okay, so here's another question. I don't think there was anything said about how proofs of knowledge relate to arguments and zero knowledge. Are there any interesting connections there? Aline is asking.
Yes, there are many, and I didn't talk about it like I didn't talk about many other aspects. For those who are interested, I mean, I described everything in terms of proving claims, but people studied, and it's very valuable, especially in cryptography, to study not claims that some object has a property, but claims of the type, I know something. And there are connections, and I'm just not, not the time to go into them. Yeah.
Okay. Another question, good question by.
Let me just mention part of the question had to do with arguments. These arguments that are different than the arguments I'm talking about. There are systems in which there are limits on the prover too, and there are more connections. And let me not go into them now. Maybe after the talk. Yeah.
Next question, is it that PCPs let you find the bug in the proof or merely detect its existence? At a high level, seems like only detection is possible unless you can do some sort of divide and conquer search. And I'll add to that, do such techniques or similar to them allow you, to recover easily pieces of information, find bugs and things like that?
Yeah, so again, it's an excellent question and requires a long answer. It depends on your PCP. You can design a PCP. I mean, most PCPs are their sole purpose is that you catch a bug. I mean, for most people, they will be happy. Users of software, they will be happy to know that a computation that was done for them was done correctly, or for referees of long math papers, they would be happy to know that there is a bug. Yeah, they find the bug. I mean, the spot check is a bug. It's a bug in the PCP. It's not necessarily directly translated to a bug in the original proof that was transferred to a PCP. So PCPs are just a particular format for writing proofs. And in this format, you detect a bug, and detection is, you put your finger in it there. So it gives it to you. But if you think about where was the bug in the original mathematical problem, or which was the gate that made the error, that all depends on your PCP, and, approaches like divide and conquer and so on may be doable.
Another question, a terrific one, by Bengt. How close is the correspondence with an error correcting code? Is there a specific code that is effectively used? I'll add to that, can all good error correcting codes be used?
Yeah, so it's a very good question, and I already warned in the beginning that you think about error correcting codes is just the beginning of an idea that is essential, but it's far, far, far from what's being done to construct a PCP. I don't know of any general construction of PCPs from any code. Specific codes are used. We know how to use very different codes for different PCPs, but I don't know that there is a general one.
Okay, and last question for this part. Are there instances where a proof by contradiction is more efficient than verification, or are proofs by contradiction accepted in any areas?
So it's a very good question, and it goes back to the definition of proof systems. It doesn't matter a proof by contradiction, a proof by just design your verifier. It doesn't matter. All of them are good. Just have a proof system in which the verifier is efficient and it's a good proof system. That's all you need. We are not in the logic framework. I mean, stepping out of the logical framework is a powerful thing. This is going back to the logical framework. We don't need to be there.
Okay, so we're done with this part of the questions. I mean, we're already past the hour.
Yeah, so I have 2 slides more. And then I'll be done. So let me conclude the talk. I just want to say about this, again, this is a revolution. The impact it had on optimization in particular was revolutionary, and so on coding and complexity theory. And I mentioned that it's very important in technological applications. But I want to just put 2 more slides about the next step in this, the train of complexity theory that doesn't know how to stop. More proof systems. So first I want to give you a 1-minute summary of quantum computation. Quantum computation starts with the same axiom like with randomized computation. It seems that nature provides us with access to quantum phenomena. So why not use it in algorithms? That's basically what Feynman and independently Manning suggested in the 80s. They said, let's build computers that manipulate quantum superpositions. It seems that nature allows it, so computers can do it. It took time to formalize, and complexity theories gave name like everything. There's a class of things that are solvable by efficient quantum computers, and they are at least as powerful as the probabilistic ones, so studying their power is interesting. And somehow nothing much happened until Shor came with his bombshell of proving that the very basic assumptions of cryptography, factoring in discrete logarithm, being hard, actually have very efficient quantum algorithms. And this suddenly, frenzy attempts to develop lots of things happen, finally building such computers. And so far, billions invested, and I won't talk now about where it stands. Cryptography decided to brace itself and prepare for this and start looking for other hardness assumptions that are not broken by quantum algorithms. People try to develop more quantum algorithms so far, to demonstrate the excess power in it. There aren't too many examples. I mean, of course, many more, but not as one could hope. On the other hand, complexity theory is at a field day. There are new models. And that's my last slide. You can define not just quantum algorithms, you can define quantum proof systems. The only difference, you let the verifier be an efficient quantum algorithm. And the prover, of course, needs to be quantum to interact with them. And then people define the analog of IP and many prover IP in the quantum world. And amazing characterizations. On the one hand, if you have one prover, then you don't get more than with the probabilistic provers, strangely enough. But if you have two provers, many provers, maybe 5, I don't know exactly the number they need right now, you get not just non-deterministic exponential time, you get all the recursively enumerable sets, the set, the class I mentioned in the beginning. You can compute not only everything computable, but everything provable to finite algorithms. And this has amazing implications in math and in quantum information theory. When you talk about quantum algorithms, what you're really trying to understand is the power of quantum entanglement. So this says that, the halting problem, the non-computable problem, can be computed, can be verified by efficient verifiers, because what they really prove is that it's equivalent to another problem that is well studied. It's just the value of a non-local game, which I'm not going to define, but some of you who remember the Bell inequalities and the Einstein-Podolsky-Rosen experiment to test quantum mechanics, that's the type of thing I'm talking about. And in mathematics, it turns out, it was understood before this result, but this connection is amazing. It's sort of mind-boggling. Is that a consequence of this result is a refutation of a long-standing and believed conjecture by Korns about von Neumann algebra, very basic conjecture. So you do this, you play these games, and you define these proof systems, and you try to understand their complexity and look at what comes out. So let me summarize, close with that, and leave you with my book as well. You can find it on my website. And my favorite proof system. Thank you.
So, Avi, I want to thank you on behalf of all the listeners, and I want to thank the listeners for asking terrific questions. I'll mention that if you want to watch more stuff that has that talks about various informal aspects of proof systems, be it ZK or recursion or how they go into blockchains, then please you can look them up on. There are already 15 previous Stark at Home episodes. If you want to write programs that will then be converted into proof systems, then I highly recommend going to this website and playing with code there. This code that you write can then be generated into proofs, succinct proofs via Starks that will go on blockchains. And if you want to hear more on why and how writing code in this framework called Cairo has anything to do with some of the stuff that Avi was talking here, then you're welcome. This will be the topic I'll talk about next week. I've posted the links here. We'll have another Stark at Home in a few weeks. So thank you all very much. And most of all, thank you, Professor Avi Vigderson.
I'm happy to answer questions, as much as people want. If they do, you can either take me off or I can, stop sharing the screen, or if people want to ask questions about the talk, I can keep it.
Okay. Anyway. So anyone who wants to ask questions, I'll stick around as well. You can use the ask a question. I'll start with one question that interests me that I said, and others can post theirs. So a little bit about your journey into complexity theory. How did you get into it? What keeps you going on it? And what is it like to be a theoretical computer scientist?
Let me stop sharing. How do I stop sharing?
I stopped it. Don't worry.
Good. We can go back there, right? I mean.
Yeah. No worries. Yes.
Yeah, I'm really lucky because I always wanted to do math in college, but my parents thought that maybe if I like math and maybe I want a job, then maybe I should instead go to computer science, like I'm sure many of you heard. I'm of course talking about the mid 70s. And I was lucky to go to the Technion, and there we had a teacher that Shimon Even just inspired us about in his courses on theory and algorithms, and also just amazing classmates that are still colleagues of mine. So that was the beginning, and then I got to Princeton and started doing research with under Dick Lipton, and it just captivated me. I mean, the being at the time a new area, but one of the things about complexity theory, I'd say, especially its interaction, its two legs, one leg in mathematics and one leg in computer science, is an extremely fruitful place to be, because on the one hand, in computer science, technology is changing all the time, and lots of models suggest themselves, and they can be parallel and distributed and probabilistic and online, and lots of models suggest themselves as to be studied, also to be implemented, and cryptography, of course, properties of programs, and so on. And on the other hand, you have tools in complexity theory being part of mathematics. There are ways to argue about all these things. There are ways to prove theorems about them. There are natural ways to formally model them and progress from there independently of any practical applications. And I think the combination of the two is amazing. The products we saw already are amazing, and I'm sure there are more. So I'm never bored. I'm always having fun.
Okay, here's a question, and so please type in your questions. We'll answer the ones here, and then we'll wrap it up. The formalism has in the multi-prover setting, each prover prove the entire statement. Are there notions of interactive proving developed around making proving more practical, where valid NP statements proof generation is distributed across multiple provers who do not need to interact and still efficiently verifiable and with soundness guarantees? So can you attribute the proof generation among multiple independent provers who are not interacting? This is a question by Harish.
So first I want to correct something in the first sentence. It is not that every prover has to prove the entire statement. This is not what multi-prover interactive proofs are. They just together have to convince the verifier, and he just decides what he asks them. He doesn't have to ask them, you prove everything, you prove everything. In fact, that's not what happens, because it cannot happen in proving statements whose proofs are exponentially or longer. It just each proves very small part of the question of the proof, but in a way that only true claims are accepted and others are rejected with high probability. So that's not. So in a sense, it is the task of convincing the verifier is shared by the provers, and in each interaction, with the verifier, only small pieces are done. So automatically, what you say is true. People looked at more general things about doing it in a distributed setting and so on, and it's a huge field. Yeah.
Okay, so with this, we answered the questions, and so I want to thank you so much, Avi, for taking the time and talking to us here, and I want to thank the terrific audience, and see you on next Stark at Home episode in a few weeks. Thank you all very much.
Thanks.
Okay.
Thanks. Fun being here. Bye.
Bye.